Good afternoon. My name is Thomas Gernet. Welcome to Hopkins at Home, and thank you for attending this session. My presentation today is on the use of computational modeling to design structures for fire safety. Today, I'd like to discuss how structural engineers can design buildings to withstand fires. We will see that numerical modeling with computer simulation plays a key role in supporting structural engineers in this mission. To understand what these numerical models are and how they work, I'd like to show examples of research to model the response of new materials exposed to fire, research to simulate the fire development in buildings, and examples of modeling of the response of entire structures exposed to fire. With examples of numerical studies, we will discuss how such models can help solving challenges with fire safety, resilience, architecturally unique designs, and more. I have been researching fire as a structural engineer since I started my doctorate studies, and I find there is something fascinating about it because fire is very primitive and at the same time very complex. Fire has been an existential threat to human settlements and cities throughout history. Until the 19th century, conflagrations in cities were very destructive. Today, fortunately, with progress in building standards, progress in materials, in firefighting, and so on, our cities are much safer. But we still see major fire events, and these have still dramatic consequences, and these have a big cost for societies. So the fire problem is far from being solved. Also, with innovations in building techniques or materials, energy systems, etc., come new fire challenges. It's interesting to look at the statistics, and we find that to protect ourselves from fire, we actually invest a lot of resources. There is a study that estimates that more than 1% of the GDP is invested by, for example, the US to protect the built environment from fire. So this includes fire losses, but also expenditures to protect buildings, insurance costs, and so on. This means that there are large stakes in research in fire safety engineering. In other words, if we can do things better, potentially there are large gains to get. Looking at the future, we see trends that clearly show the fire problem being more relevant, certainly not less, with new materials used to fight the climate crisis, such as the use of mass timber for taller and taller buildings or the combustible materials, with EV cars, battery systems, with also wildfire getting closer and closer to densely built environment. We see that we need more engineering to tackle fire and find efficient solutions to make our buildings safe. Traditionally, the traditional approach to protect structures from fire is a prescriptive one. It means that there is minimal to no calculation involved. The idea is that we rely on standardized furnace testing to qualify fire-rated assemblies. And then the engineer, or in many cases the architect, can choose the appropriate rated solution from listings for these qualified assemblies. This approach is very simple, and that is both its strengths and weakness. The roots of this approach are actually more than 100 years old. And if we look at how fire casualties have decreased throughout the 20th century, it has been largely successful. So certainly it has raised the baseline for safety in our cities, in our environment. So that's a success. But there are a number of limitations because the approach is so simple, because it is one size fits all. So there is research showing shortcomings with the fact that it only looks at single elements at a relatively small scale. The fire exposure is not necessarily representative either of all situations. So there are a number of limitations. In fact, this approach certainly works well for common situations, common buildings, and when the profession has experience on the type of structure that is used. But because of the mentioned limitations, it cannot answer all questions, and it falls short when we have new systems or when we have larger structures. So alongside the prescriptive approach, structural engineers can be engaged to design for fire. Structural engineers already calculate and optimize structures against various types of loads, and fire is another type of structural load. Structures should resist the heating from fires as they resist the acceleration forces from earthquakes and the pressures from wind. Especially, engineers work hard to optimize the use of materials to make structures lighter, more sustainable, with an efficient use of resources. So it is not consistent to invest lots of efforts in designing structures and sizing members for a number of load cases, but then treat fire as an afterthought and apply a generic fire protection to the sized members and all members considered individually. This leads to a suboptimal design. So instead, the proposition is to treat fire as another load case, and it is possible to complete a holistic design and find the structural system that responds the most efficiently across the different loading situations. In this effort, computational modeling is key. Simulation can be helpful and can support this type of design. Simulation is already used for seismic and wind analysis in many cases, and the tools are available for fire as well. In what we call a performance-based design, the design seeks to achieve a required performance, and the engineers must demonstrate that the design achieves this performance. So instead of adopting a set of prescriptive rules that are deemed to satisfy. A performance-based approach is also the only solution when there is no prescriptive provisions, for example, because there is no collective experience from the profession with new systems or innovation. Performance-based design for structural fire engineering to address fire loading can bring value in a number of projects or situations. For example, I list a number of situations here where engineers would want to resort or would need to resort to an explicit assessment of the response in case of fire. One example is if we want to quantify the safety of a design against fire. So to complete a risk-based design and explicitly assess the expected performance in case of fire, we'll use computational modeling. To optimize the design, to size sections for optimal response across all load cases, as was mentioned, and also apply fire protection only where needed and in sufficient amount where really needed. To enable design. So in many cases, if the design goes outside of what would fit within the code, for example, because architects have created a unique design, they want exposed steel or exposed timber or simply a different configuration, well, modeling can come in support of this and make that possible by assessing and designing for fire safety. Support forensic analysis is another case where computational modeling for fire is required. Study existing structures, study the fire safety strategy of heritage structures, where again, code provisions would not be applicable or would, I would say, hurt the heritage value of the building. Controlling the failure mode. So in some cases, the fire safety strategy does not really require that the structure remains stable up to full burnout. But instead, if people have a time to evacuate, it would be acceptable to have a collapse. An example is a one-story warehouse, for example. But still, we would want to make sure the collapse does not endanger firefighters around and does not lead to spread of fire. So we can design such that eventually the collapse would be an inward failure, for example. And we'll see an example of that. On the other hand, if we do want stability until burnout, as in a very tall building, in a hospital where evacuation would not be possible, computational modeling can help finding solutions for survival to full burnout. And if we apply a prescriptive approach, we don't explicitly know and check whether that is the case. And also to develop design provisions. So these were examples of value of computational modeling for structures in fire. Now, how does that work if we want to assess the fire response of structures? Well, it is a three-step procedure. First, we need a model for the fire development. We need a fire simulation that will output gas temperatures, heat fluxes, radiation, radiant intensities, and so on to find out the thermal exposure of our structural members. Second, we need a thermal analysis, heat transfer analysis, that will compute the temperature increase inside the members based on the fire exposure, of course. And third, we have a structural analysis where now we check deformations, forces in the structure, considering the temperature increase. The figures on this slide show application of modeling to simulate a full-scale fire test that was completed in 2010 in Northern Ireland. And you see it was a wood creep fire. So for this composite steel concrete structure, the idea was really to measure what would happen, or what happens really in case of a natural fire that could develop. And modeling tools were used at each of those three steps to capture the response and eventually provide confidence that these modeling tools can work and can represent real scale what happens in a structure exposed to fire. Now we understand there is value in modeling structures in fire. Let's dive a bit into what makes these models, what is required in those models. So one key component are the material models. When there is a fire, it generates heat, and as a result, the temperature increases in the steel beams, the concrete columns, and the materials are affected by this temperature increase. The properties degrade. We need to quantify that. We need models that capture these temperature dependency. This is a continuous research need because when there are new materials, when there are new assemblies of materials, we need new models to capture that. There might be new fire hazard as well. For example, right now in the community, there are lots of questions and there is a lot of research around the cladding and building envelopes and so on, as a result of the Grenfell fire in 2017. This material response is important both for combustible material and for non-combustible material. For example, with new high-strength concrete come also new fire risk, potentially more spalling and this type of issues. So it's not necessarily that only it applies to combustible material. And as an example here, I'd like to talk about advanced high-strength steel, so which obviously is non-combustible. But these are steels with very high strengths that come from the automotive industry. And researchers are looking at applications of these in cold-formed steel building construction. Notably, here at GHU, Professor Schaefer is leading a research effort on this. So to understand the fire behavior of structures made with these materials, we must first study and characterize their response at elevated temperature. We looked at two different types of advanced high-strength steels, and we also tested regular mild steel for benchmark. In the lab, we use a furnace mounted on a loading rig, and we test specimens cut out of steel sheets. So the furnace elevates the temperature of the steel specimen, similar to what a fire would do in a building. And we then measure the strength and deformation and how the stress-strain response is affected by temperature. There are different testing protocols at elevated temperature. We can first heat and then apply the loads, or on the contrary, first stress the material and then heat it up to failure to find the failure temperature. But what's important is that we conduct this test across all temperatures of interest, and we find temperature-dependent force displacement or stress-strain response. So what did we find? Well, first, we find that the new advanced high-strength steel behave differently from the regular steel. So that is important because it means we cannot use the same models. We need dedicated models for these new types of materials. The advanced high-strength steels have much higher strength at ambient temperature, as the name indicates, but as the temperature increases, they lose proportionally more of their strength. So at some point, the benefits decrease, and we need to quantify that, and because it has implications for the fire design and the amount of fire protection and so on. Second, we quantify these variations and these temperature dependencies, so we derive equations for the temperature dependency of the stress strain and properties. These equations can be, on the one hand, proposed for consideration in future version of standards to help and support engineers in designing with these new materials. And on the other hand, we also implement these models in numerical codes to enable computational modeling. When we do these type of experiments, if we repeat the same experiments a few times, we observe some variability in the response. And if we compare what we do, we also compare with results from other labs, we observe even more variability. So there is uncertainty in the material response at elevated temperature, and there is some variability in measurements. To capture this uncertainty, the models for the materials that we will put in the simulations can be made probabilistic. So in a project with colleagues from University of Ghent, University of Buffalo, company OFR in the UK, we collected a large database of high temperature properties for steel and concrete, and we look at the distributions of measurements at the different temperatures. We found that the distribution was well captured by a Weibull probability distribution, and we proposed equations that give the parameters of the Weibull distribution as a function of temperature. So now we can code these type of material models in our computer software that are probabilistic and that capture the variability in material response. So this enables probabilistic risk assessment, also using computer models. Recently, we are working with colleagues from University of Valencia in Spain to do a similar model for timber, where also measurements show really a large variability of response at elevated temperature. So these type of models are important to performance-based fire engineering because we can systematically account for the sources of uncertainties in the predicted response. And this is an example for materials, but we do the same for example, parameters of the fire model or thermal heat transfer models. So the previous slides showed works on the material models. We also need models that predict the fire development in buildings. What happens when a fire develops in a building compartment is that it generates heat, and that heat challenges the structure. In structural fire engineering, when we simulate the response, we don't want to work with a prescriptive time temperature curve, but instead we want to model the fire development and the expected thermal exposure in the room for the members, the structure. So there are different types of fires that can develop depending on the situation, as you see at the bottom of the slide, and researchers have proposed models for these different types of fires. On fire models, the effort starts with having good data for the inputs. And probably the most important input is the fuel load that is present in the room. The fuel load is the energy that can be released in case of fire from the combustion of the furniture and content in the room. The problem is that data is very limited about fuel load because standards rely on surveyed data, but surveys are cumbersome, so they are often outdated, and just in general, there is not much data. So with a colleague from University of Buffalo, we worked on a new method of data collection for fuel load that is more efficient and facilitates data sharing. So it relies on using a tablet to take pictures of the content in a room. And then there is a web application where to upload the pictures and compute the fuel load with support from machine vision. This also helps having a standardized database. So that was an effort funded by the National Fire Protection Association, and it's an example of research effort to improve the data that we put in our computer models. Next, talking about the fire models themselves. So there are different types of models to simulate fire development. And on this slide, I present an example that applies to so-called localized fires. So a fire is said localized when it stays localized as opposed to developing into flashover that engulfs an entire room. So localized fires are observed typically in very large rooms or when there is fuel only in one part of the room. So you can think about a car park, an open car park, or an airport terminal, for example. Models for localized fires are complex because the thermal exposure conditions heavily vary with the position in the room, in addition to being transient. So one way to model these fires is with computational fluid dynamics. And then we need a method to interface the computational fluid dynamics software with finite element softwares that are used for the thermal and structural analysis, the second and third step. In the research on this slide, we work to benchmark different methods to model the localized fires and to interface with finite element models against different experiments that we had. And so this, we obtained a good agreement in predicted temperatures in the steel. So we showed that, again, we have those computational tools and we can use different methods such as the adiabatic surface temperature or outputting the gas temperature and radiant intensities to capture both convection and radiation that would occur at the interface between the fire and the structure. So these coupled fire thermal models can be applied for structural fire design. For example, here is a car park structure made of steel frames with a concrete slab. And it's an open car park, so with lots of ventilation. With the models that we showed on the previous slide, we can study different scenarios of vehicle fires. So we used CFD to model the fire, and then we used finite element analysis to get temperatures in the steel members. That can help to determine how much thermal protection the steel members need. It is found that it depends on their location respective to the car park spots and the vehicles in fire. It depends also on the size and section factor of the members and the applied design loading. Also, sometimes steel profiles are galvanized, and this changes their emissivity, so it changes the radiative heat transfer, and that's also something that we can take into account. Using the models for fire development with the models we discussed for materials, we have the components to model structures in fire. So the modeling of the behavior of a building structure in fire is a three-step procedure. One, we model the fire development, and we take inputs such as fuel load, as we've discussed, but also geometry, ventilation, and so on. These fire models give boundary conditions for the second step, which is the thermal analysis to get temperature distributions in the structure. And third, we model the response of the structure under loads and heating. In that third step, we need models for the materials, and this is based on experimental testing, as we've shown, and then computational constitutive models that go into the finite element simulation. So for steps 2 and 3, the thermal and structural analysis, we commonly use finite element method. And one software, amongst others, that can be used to solve this problem is called Sapphire. That is a software that we at GHU co-developed with a scholar from University of Liège in Belgium, Professor Jean-Marc Franzen. Sapphire is widely used in structural fire engineering, both in academia and by designers. So when using a finite element software like Sapphire, the fire models serve as boundary conditions. And then Sapphire reads outputs of fire models, for example, gas temperature or heat flux, radiant intensities, and it assigns these at the boundaries of the structural members to complete the thermal analysis. Sapphire then computes temperature distribution over time during the fire, and then the structure is modeled with its different members and loads, and the software computes the behavior, displacement, internal forces as the temperatures change in the member as a result of the fire. So Sapphire and those type of software include different materials, finite elements, so for walls, beams, columns, slabs, etc., all the components in the structure. And there are also different methods of interfacing with fire models. Well, here is an example of design of a structure to withstand fire loading. We'll now put together all those models we've seen and show how numerical modeling can be leveraged to identify an efficient solution and to demonstrate performance in the fire situation. In the 1990s, there were a series of very important experiments for the field of structural fire engineering conducted by the BRE in the UK. They are referred to as the Cardington fire test. And in these experiments, it was notably observed that some structures survived, meaning they remained stable, throughout a fire, even with some steel beams being unprotected. So if you have steel beams that are unprotected in a large compartment fire, such as the one that was tested, the temperature becomes much higher than what calculation would predict as the failure temperature of the beam. You get temperature of 800, 900 degrees C in those steel beams. So there was no way for these beams to be able to withstand the loads as expected in a regular design. And therefore, the question was, how did the structure survive? So the reason is that structures are not just single beams and single floors and elements in isolation. When we do a standardized furnace test, we look at them in isolation, but in fact, structures are systems or assemblies of these elements to work together. So with proper design, it is possible to harness a system-level behavior in this type of composite steel concrete structures. And when we have large displacements developed under fire, alternate load paths can be found in the structure, can develop to conduct the loads to the ground. So there is robustness, in other words, in that structure. This is what happened, and the mode that was activated, this alternate load path, is called tensile membrane action. Here is how tensile membrane action works. So we are talking about steel concrete buildings. We have steel beams that support a steel deck, and concrete is poured over the deck. There are studs connecting the beams and the concrete floors, so the system works as a composite. And note that's important that there are also reinforcement steel bars embedded in the concrete. Different countries have very different practice in terms of how much reinforcing bars they use. These bars will be key. Now, in a prescriptive fire design, all steel beams in the building would require fire protection. But as observed in the BRE experiments, some of this fire protection may be unnecessary when considering the structural system response. So here, we apply fire protection only on the peripheral frame members, not on the secondary central beams. In case of fire, these secondary beams get very hot, so they deflect, and the composite slab follows. But as the deflections increase, the reinforcement bars in the slab are put in tension. And so these reinforcement bars, now they will resist additional vertical deflections. This means that the loads that used to be carried by the central beams now has been transferred to the steel bars embedded in the concrete. The advantage is that the bars are embedded in the concrete, so they are protected from heating. They remain cold much longer than the unprotected steel beams, obviously. But so this is an example of alternate load path with a new mechanism. The slab deflects as a membrane with a tensile zone at the center, and so that's why it's called tensile membrane action. Since observing this behavior in the large-scale experiments in the UK, the behavior has been reproduced both in laboratory tests and in large-scale natural fire tests. The community has also validated numerical models to capture this behavior. One of the modeling challenges was notably to develop appropriate models for the materials for the concrete, which is something we discussed, in order to capture possible failure modes in the concrete slab. Well, we discussed it with the example of advanced high-strength steel, but so similar efforts were needed for concrete in this case. On the slide, you see displacement time curves obtained with the software Sapphire when modeling a laboratory test conducted in New Zealand and a large-scale test, the one showed previously in Northern Ireland. So good agreement was achieved between the model and experiment. Now, using these tools and this understanding of the system response, in a study, we looked at designing a prototype building to take advantage of tensile membrane action in fire. The building is a 9-story office building. It has steel frames and composite steel concrete floors. According to the prescriptive requirements, a 2-hour fire resistance rating is required on the steel framing members. So we completed a performance-based fire design. And in that procedure, first we must define performance objectives. What is it that we try to achieve with the design? For that building, we decided that the building had to survive to full burnout, so remain stable, without intervention, without any other layer of fire protection, so no sprinklers, no fire brigade. We want the structure to resist a fire. And we wanted to consider very severe or exceptional events in case of fire, which include a fire spread across the floor plan, and also the case of column loss followed by a fire, which would represent a blast followed by a fire. So 3 fire scenarios were defined, and for each simulation had to show the ability to survive to full burnout. For each of those fire scenarios, we need also a fire model that quantifies the thermal exposure. So we look at high percentile of the fuel load for the office building. We applied a so-called zone fire model. And note also that there are other parameters that will influence the severity of the fire, such as the availability of oxygen. So if there is more ventilation, the fire might be shorter but more intense, as opposed to if there is a shortage of oxygen. So we run sensitivity analysis, and eventually we define two fires for each scenario for different sets of parameters. We also have an assumption when we have to have fire spread in the floor plan, so we have a delay between ignitions in adjacent compartments. To design the structures in fire, we first looked at a subsystem or a panel. So this includes peripheral frame members, secondary beams, and the composite slab. And the objective is to design this panel to develop the tensile membrane action in fire. So in fact, we work, you see there are 5 curves, which are different iterations on the design. We worked on a trade-off where we remove insulation from the central beams, but we have to add reinforcement bars in the concrete to carry these membrane forces. So we use numerical simulation and check different designs on this subsystem. Eventually, we find one that survives to full burnout. And next, after this pre-design stage, now we move to the entire structure, and we're able to model the building. And with this entire system, we actually have a simulated response, which is more favorable than with the single panel. The reason is that we have even more restraint and more redundancy when we look at the entire building. There are different panels, different compartments, so when there is fire in one compartment, the deflections of the heated floor, for example, are also restrained at the boundaries by adjacent panels. So we are able to refine further the design and find an even more efficient solution, but still taking advantage of tensile membrane action. So with no insulation, no fire protection on the central steel beams. Next, we use the same model to check the fire spread scenario. And in order to survive to full burnout, because now the scenario is more severe, we need to re-increase a little bit the amount of steel reinforcement in the slab. So the same strategy, harnessing tensile membrane action works, but in terms of detailing, we need a little bit more steel in the slab than with a single fire. And that's because we have multiple panels, multiple sections of the floors that are heated in the same event. And you remember we had three scenarios. So the third one was a column loss followed by fire spread. And here again, we find a design that works, actually the same as with the fire spread scenario. So what's very interesting here is that we observe that the tensile membrane action is already activated when there is the column loss. So this load-bearing mode, this alternate load path that we found was robust to resist fire is also something that helps to resist a column loss, according to the same principle of large deformations and activating this tensile capacity in the steel reinforcement. So that means that here we really achieve structural fire resistance through structural design, through a robust structure, and that works across extreme events, across accidental loading scenarios. This system for structural fire design has been used in actual projects. So the buildings shown on this slide, they leverage tensile membrane action in the composite floor, and so they were able to remove thermal protection on secondary steel beams. So there is clearly an economic benefit. It also can be a sustainability benefit with less insulative material. But at the same time, in terms of safety and of behavior, really simulations show a lot of robustness, as we've shown previously. So even if we go to fire spread, to column loss, etc., properly designed, it can survive to full burnout because it's really a robust behavior. So this was an example of designing structures for fire with a performance-based approach and the potential benefits that can be gained and the fact that it is now used in practice. In the US, there was a recent technical report published by the Structural Engineering Institute of the ASCE, which describes the application of performance-based structural fire design to 4 buildings by 4 structural engineering firms. And they used computational modeling. They described a similar approach as the one I just detailed here. And they also leveraged tensile membrane actions in several cases to design for structural fire resistance. So the link is here, and I encourage you to have a look at this report to see an application to say the case of US structural design. Now, there are other types of benefits of modeling the behavior of structures in fire and using computational modeling. And without going into details, I'll just mention a few. So, for example, this can be used to address important safety questions for building occupants and also for firefighters. Questions that cannot be explicitly answered by a prescriptive approach, but instead require numerical modeling. For example, prescriptive designs do not contemplate the cooling down phase of a fire. So if a building owner wants to basically have a building survive to full burnout, it would need a performance-based approach to check that, to demonstrate that. So we have a few research projects where we looked at the behavior of columns made of concrete, timber, throughout heating and cooling phases. And what we find is that there is a continued heating during the cooling phase of a fire due to the heat transfer processes. And so there is a continued risk of collapse, including during the cooling phases. So we studied this behavior, and we can provide design methods, again supported by numerical modeling, to design for full burnout. Another application that I mentioned at the beginning of this talk was the collapse mode. So in some cases, we want an inward failure mode for buildings after everybody was able to evacuate, obviously. And you see that there's been research also, both experimental and then numerical, to make sure that the structural system is such that in case of fire, and if a failure were to occur, it would be an inward failure, which is better to prevent fire spread and for safety of fire buildings. So we worked on understanding, for example, how connections and the stiffness of connections in rotation could influence this failure mode. That's what you see at the bottom of the slide. Beyond safety, modeling is used to explore issues of resilience. So structural design now looks at achieving additional performance objectives, such as the ability to be reused after an accident, for example. And that is done also in fire. So here on the right, you see a project where we worked with the NIST to study the post-fire performance of cold-formed steel walls. These walls with strap bracing were first tested at the NIST under fire, and then after the fire event, they were tested to failure under lateral loading. So the objective is to understand in what situation such walls could be reused after a fire, whether they would need to be repaired or replaced. And so in the NIST full-scale testing, they can do a few configurations for a few types of fires, but then with our numerical modeling, we work with them to do the numerical modeling part, and now we can study that problem with parametric analysis and find out guidance for engineers for post-fire reuse. So these were some illustrations, some examples of benefits or applications of modeling in structural fire design. There are more. For example, in some research projects, scholars have looked at preservation of architectural heritage, so using modeling to find strategies to make heritage building safe. And of course, we don't want to use prescriptive requirements. We don't want to use necessarily compartmentation or application of fire resistive or fire protection material, because that would hurt the value, the architectural value of those buildings. So we use modeling to find out alternative solutions, but make sure that they are fire safe. And also to enable design. So there are examples of iconic designs where modeling was used to, for example, use exposed steel in a facade. So that was a project led by Dr. Hopkins in the UK, and using sapphire, they were able to justify this design. And at the bottom right, you see an example for a bridge study done by Eric Tonicello in Switzerland, who studied scenarios of truck fires on a bridge, because it was a bridge with very high cost, lots of value, and with a unusual design with intersecting steel arches. So modeling was used to check the behavior in case of fire. So to wrap up this presentation, I've talked a lot about what we could do with numerical modeling. I'd like to mention a few barriers and opportunities and research needs also in that space. So it's clear that it's a continuous effort, that we can always improve these models, and notably when there are new materials that come to the market, there might be new fire risks. So it's very important to study those innovations and develop models that address the fire risk, and that can be incorporated in the structural fire models. So right now, some of the most pressing questions are with the implementation of some, I would say, sustainability-friendly materials. We think, for example, of mass timber in tall buildings. So there is a lot of interest in that direction, but it needs to be carefully studied and just properly designed for fire. And so those tools that we've been discussing can be really helpful in addressing these questions. There are also opportunities from incorporating advances in science and engineering from other fields, and just in general with the progress in computational power, also we have more opportunities for modeling. One important barrier that is worth mentioning lies with education and competency. So the fact is that structural engineers are not typically trained to apply these methods and not typically trained to explicitly design for fire. So in order really to reap these benefits, there needs to be education and showing how to apply these methods. But it's not only with engineers, it's also there needs to be a better communication of the potential benefits and of the rigorous fundamental on these methods, communication toward building owners, authorities having jurisdiction, and so on. So the different stakeholders must be more familiar, and that's on us, structural fire engineers, to facilitate that, but must be made more familiar of this alternative performance-based fire method in parallel with the prescriptive method, which certainly is there to stay as well. So educating on the methods, what lies beneath and what is rigorous in those methods, and also the potential benefits of making the effort. So fire hazards governs many aspects of design in a building, and it is not going away, so it needs to be carefully addressed. There is one road which is prescriptive. It has improved safety across the board, so it has been successful, but alongside there are opportunities because methods and the science and the understanding has improved, so we can do also design for fire based on analysis of the simulated response. And in many situations that can bring value, that can deliver value, and structural engineers should embrace this as they've done with other types of structural loads. Computational modeling is a key enabler to make that happen. It is based on models for the fire developments, models for the materials and for structures. We've shown examples throughout this presentation. And notably, finite element software that combine the thermal and structural analysis are available and can be used for this purpose. So with models, it's possible to find design solutions that are more efficient than prescriptive ones, or to find solutions when prescriptive ones cannot be adopted. It's also possible to study the shortcomings of prescriptive solutions. Notably, we think about geometric changes due to thermal expansion. When we are thinking about long span floors, for example, it can lead to issues that are missed by the prescriptive method. So these type of things are looked at carefully by structural fire engineers with numerical modeling. And finally, to reap these benefits, it's important to communicate and educate about this alternative option. And the onus is on structural engineers, not only to embrace it and be able to implement it, but also to be able to explain the background, the method, and the value of this approach. I want to thank you for attending this presentation. Thank you so much to Hopkins at Home for hosting us today. And I would like to acknowledge the listed sponsors who funded my research. This concludes my presentation. We'll now start with the Q&A session. I am now reading the first question. Could this modeling be used after the fact in cases where a fire has taken place to hypothesize about what started it? So yes, this is a very good question, and the answer is yes, certainly. Modeling can be used and has been used in forensics analysis to understand the sequence of events that led to a structural collapse. Instead, in terms of hypothesizing about what started it, yes, but then, of course, that would be more on the fire modeling side, looking at the fire reaction of the materials and hypothesizing on the location where the fire could have started and so on. In terms of the structural modeling side, if we are looking at a failure, there have been examples of investigations, for example, thinking about the World Trade Center, where this type of modeling was used to hypothesize and try to understand the sequence of the events, or where failure would have started, notably with the effect of thermal expansion, in addition to reduction of material properties, of course, and then recreate these, basically this chain of events for the structure. So yes, absolutely. Forensics analysis is a great example of application and use of those models. Another question, does human behavior figure into the simulation at all? Yes, again, a very good question, because I have not mentioned it. It was outside of the scope of my presentation today, but fire behavior and evacuation are very important aspects of fire safety engineering as well. It is not common to explicitly link the human behavior analysis and the structural fire response analysis. In general, these are, I would say, separate disciplines, although people talk with each other. But when we look at the response of the structure, we will want to make sure that the structure remains stable for sufficient amount of time for evacuation, but we will not explicitly look at I would say, the movement of people and the evacuation problem in that simulation. That would be kind of a constraint, this minimum time or requirement. But when we do also study resistance to full burnout, it's also because, again, as a constraint, we are very much aware that in some situations, evacuation is not possible. So if we're talking about a tall building, for example. So to summarize, yes, human behavior is very important. There is an entire field of research in fire safety engineering dedicated to that. Usually, the coupling is with structural fire simulation is in terms of a constraint, a performance objective, I would say, but not a single simulation incorporating everything. Have you used neural networks at all when developing these algorithms? That's interesting, an interesting point. So it links to something I said at the very end with the opportunities. So we've seen neural networks and more generally artificial intelligence used in a number of engineering fields, and we've seen that it can bring benefits. So in the structural fire engineering community and fire safety engineering community, we as a community have started to look at these applications recently, and notably starting with some very complex phenomena that occur in some parts of the problems that for which I would say analytical and mechanistic-based models have not succeeded in giving an answer. For example, I have a colleague at Clemson University who's applied artificial intelligence methods to try to predict spalling in concrete. Spalling is when you have an explosive fall off of some pieces of a concrete section. And it's caused by a complex combination of thermal stresses, mechanical stresses, and pore pressure buildup with the vaporization of water. So it's extremely complex multi-physics. And for this type of phenomena, it would be very interesting to see if AI or neural networks can help, can support modeling. With my team, we've started to look at some application also of machine learning for thin-walled steel beams and columns, for which the instability phenomena at elevated temperature can also be complex. So in summary, it's not something that has been widely embraced or that has really changed the way we do the global modeling and the global analysis of the problem, but it has started to permeate punctually to solve or to look at some specific problems that have been a hurdle for structural fire engineers over the years. So it's a trend that is starting. I had a question about how was the algorithm outlining fire behavior determined? So yes, thank you for your question. So there are different types of fire models, and in the presentation, without going into too much details, I showed applications of different types of models. But if I understand the question correctly, when you refer to outlining the fire behavior, I will assume it's in terms of the fire growth and the spatial development of the fire. So it's still very challenging to predict fire spread between compartments, for example, or even fire growth and traveling fires in a compartment. There are models that do that, but in the applications that I've shown, in most cases, it was an assumption, meaning, for example, in the fire spread scenarios, we assumed that fire was spreading every 20 minutes, it was starting in the adjacent compartment. So that was not a predictive simulation based on physics. It was an assumption where our goal was really to check the effect. What if we have a fire spread? So how would that challenge the structure? And we know from observation that, okay, we have seen fires that have developed in multiple compartments across a floor plan. There are a number of reasons why that could occur. But we are not there yet where we can really predict whether that would occur, because it would require incorporating just all details, also of non-load-bearing components between compartments and different processes. So in general, that is still treated as an assumption, and we check consequences. In what stage of the process do most architects or designers use this model? When starting or after they've put something together? Yes, good question. So I think it depends. From my experience and from talking with practitioners in the US, it is still very rare, it's exceptional that this approach is used by default when starting and initially in a project. The decision is made to do performance-based fire design. It is starting to appear, but it's still very much the exception. But then it happens that in some projects, these models can come and save the day at the end of the process. For example, if something was missed in the design, or if there needs to be a change in the design while the building is going up. And so there have been cases where that's indeed when the models have been used, and we're able to find solutions. In other countries, there is more of a tradition to do this type of design. For example, the UK certainly come to mind. And there are a number of projects where there are structural fire engineers consultants, part of the structural engineering teams. So they work together, and from the beginning, they will find a solution that works well also for fire. And so I think there can be much more synergies there, obviously, because details of the structural design can be modified also upstream to make a design more efficient for fire. And by the way, in the technical report from ASC that I mentioned in my presentation, the structural engineering firms were looking at the two configurations, meaning they looked at the building already there and seeing if they could change something that would improve the fire performance. And then they looked at the same building, but where there was freedom from the start, from scratch, to make a structural fire design. So that's a very relevant question, and the two have been studied, actually. So let me see, I think we have a last question. What's your opinion on the importance of a real-time appraisal of a fire in the simulation model? Meaning the reduction and increase of fire in relation to combustible materials with wood initially serve as a dead load. Yes, thank you. So let me make sure I understand the question. So when we use the fire model, so there is a certain amount of combustible material, there is a fuel load, which is characterized also with its heat release rate, and all this will influence the fire model, the fire development in terms of gas temperature, heat fluxes, and so on. So if I understand your question, it's about the reduction and increase of fire in relation to combustible materials, which would initially serve as dead load. So we account for this combustible material, which is present, which serves as dead load in how much energy that brings to the fire. So this coupling definitely is there. We don't do the I would say, the reverse coupling of reducing the dead load because some material burns. So that usually is not accounted for, is conservatively ignored. So we assume the dead load that was there at the beginning of the event remains there. But so definitely there is a real-time appraisal of how much heat is available to elevate the temperature and so on from the combustion of the combustible content. And by the way, at this time, there is a lot of research on understanding how that works with wood structural members, because there, the wood beams or wood CLT floors can contribute to the fire. They will bring heat to the fire, but as they become consumed, also, of course, the load-bearing capacity will be affected. So in that case, we have this two-way coupling that has to be accounted for in the models. So certainly. So there are lots of coupling between the three steps that I outlined: fire, thermal, and structural. In most cases, the simulation is sequential. So we do the fire model, that is a boundary condition to the thermal analysis, and then that is a boundary condition to the structural analysis. However, there are cases where we need also feedback. And the potential change in parameters as a result of a fire, what would guide assumptions such as a 20-minute fire spread you earlier touched on. So yes, I think I mentioned that briefly. But so, for example, I can give you another example quickly. So in terms of fire models, the amount of ventilation and oxygen will be instrumental in the intensity of a fire, because if there is more oxygen available for the combustion, there is also more heat released at once. When there is a shortage of oxygen, we talk about ventilation-controlled fire. Some of the combustible gases cannot react from the combustible material. So either there is external flaming, they go outside, or simply they stay in the room. So one of the parameters that is relevant is whether windows are open or closed. And of course, we don't know that when we do the model. So usually we use sensitivity analysis. And this is what guides our decision. We look at what would be the worst assumption. And it's not always that all windows are open, because if you have excess air, it can cool down also the environment. So we have to look at those through sensitivity studies to find out the most critical cases. But I think that I was able to answer, at least partially answer, to all questions. I see also that I think we have reached the time. So I want to thank you very much again all for attending. Again, many thanks to Hopkins at home for hosting us. So my name is Thomas Gernet. I'm an assistant professor at Hopkins University in the Department of Civil and Systems Engineering. And thank you and a good afternoon to all.